All right, you know how to do all of these. They're simple enough because it comes from Honors Chem, but I do realize that a lot of you maybe forget it because it's been a while since you learned it. So I'm going to go over it in detail with you, but there's only one type of every problem. You'll notice that the little packet is kind of small today, yet it'll take us some time because you're going to practice all the problems. You have lengthy amounts of homework to do, but like I said, you only have to do the last limiting reactant problems for sure. And then the answers are all given to you so that you can check your work and see if you're understanding it or not. But certainly come back with some questions if you're not sure. So we'll do this today, but as we're practicing, I want you to have your calculators, but I don't want you to use them until after you mental math it. So we're going to practice a whole lot of estimating what the answer should be and then using our calculators to see if we're right. So the first part we'll go over is the mole. So this is Avogadro's number. If you notice, we're going to use 6.022. What do you need? You guys didn't get packets? No. Everybody has a packet? So this on your equation sheet is now going to add an additional place, the thousandths position. So just if you're using free response, make sure you use all the digits given to you on the AP exam. If you're doing this on multiple choice, just use 6. You don't have to go any further than that. So we all recognize that this number is really, really large, right? But how large is this number? And I thought this was a great example I read in my notes. I have 2 examples. The first one says, this many quarters, like coins, would cover the surface of the earth to a 2-meter depth. 2 of these. That many quarters. Wow, you guys seem like you knew that. You're so excited. That's not amazing at all, huh? That's amazing. That's how big this number is. This one I thought was even better. This many grains of sand, okay, we all know how small sand is, could cover the entire state of Texas to a depth of 15 meters. That's a lot of little grains of sand. Does that put in perspective how big this number is? Wow. Let's all say wow. Wow. That's great. Okay. But we need a number this big because how can we discuss how many water molecules are in my cup of tea, right? So molecules, atoms, ions, formula units are so incredibly small that we need to relate them to something larger, the mole. We can measure a mole of substance. We can weigh out a mole of substance. We can't weigh out a molecule. So we use the mole. All right, the mole is equal to 3 things. If you recall, we'll make a little quick mole map. Maybe you'll make your own in your notes. It's equal to 3 things, 22.4 liters, 6.02 times, 22 times 10 to the 23rd, all of those particles, and then grams from the periodic table, which is mass. The types of particles we can have are atoms, ions, molecules, and formula units. Because not every particle is the same type, right? These are different from each other. So lots of you forget how they are different. So take a moment with your group and give me an example of each of these types of things. Atoms are specific, right? They're different than ions and molecules and formula units. So for example, I want you to give me a molecule is like PF6. I want you to come up with your own example. All right, work with your group. All right, so just make it known, an atom is anything that is an element on the periodic table. Ions carry a charge. Molecules are covalently bonded, so it's 2 or more nonmetals. Formula units are ionic bonds with a metal and a nonmetal. Do you need me to move this, the screen? Is it in your way? You sure? Okay. So what this slide is saying is that we can calculate how many neon atoms there are using Avogadro's number, and then using mass from the periodic table, we can come up with the weight for it. So you know how to use the mole map. When you calculate masses, you add them up from the periodic table, use parentheses when necessary, you know that. Okay, we're going to just do this, and we're going to try it without a calculator. So let's recall how we do molar mass. How many moles of sodium chloride are there in 48 grams of sodium chloride? So make sure that first you identify your known. You're starting with 48 grams of NaCl. And whatever you write here has to go down here, so we know grams goes in the denominator, and then moles goes up here. of NaCl. It is always 1 mole when it's written with anything other than a mole. So we're going to have 1 mole to grams. We're going to go look this up on the periodic table. We're going to calculate its mass, 22.99, 35.45. If we're doing this without a calculator, we certainly would round, but we could even add these up. And now we're going to do our math without a calculator. So 48 divided by 58 essentially is what we're looking at, right? What should your answer sort of be? Less than 1, greater than 1? Definitely less than 1, right? Everybody look up here because your test, the only hard part about the multiple choice is honestly the math without a calculator because I'm confident you can do this, right? So what is 4th grade math here? What's easy to do? Like easy division. Yeah?
48 divided by 6.
Yeah, what's 48 divided by 6?
8.
That's so great. 6 times 8 is 48, right? All right, so if I do 6 into 48, that's like 8, but it's like 58, so like 60 into that, so it's 0.8, right? Like if it was 48 divided by 6, then that would have been 8, and when I add that 0, I have to move my decimal place over. So it's 0.8, which is less than 1, so the answer is approximately 0.8. And your actual answer is 0.82. If you calculate it on your calculator. All right, next one. How many grams of C2H6 are there in 18.7 moles of C2H6? So set this up, but this time make sure that you write your units so that you don't put your grams in the wrong spot. Try to calculate it without a calculator. So you should get, using mental math, roughly 561. The correct answer is 562, I think. Here it comes, 562 grams. So you just set up your problem. I just did mental math, but wrote it out. 18.7 times 3 is 56.1, but then when you add that 0, you need to move it over once to the right, so it's 561. All right, moving on. So now we're going to go within our mole map. We're going to go from how many grams of substance there are to how many molecules of water there are. Recognize this, that the known and the unknown match each other. In other words, water is the same thing as water, right? I know that makes sense. But the next problem we're going to do, it's going to ask you how many hydrogen atoms there are. So recognize that problems can go an additional step, that you need to look at your known unit and your unknown unit and see if they match. If they match, then it's just a simple mole problem. All right, so let's try this one, and then we'll do it without a calculator. So you should have this setup already worked out, and you should be able to estimate that your answer is roughly in the 500 range. How many of you got there? Roughly 500s? No one? Maybe I'm thinking of the wrong example. Oh, yeah, I'm thinking of the wrong example. Sorry, because there's a times 10 to the 23rd there. All right, so let's try it. I would do 56 times 6. So 36, 33 times 10 to the 23rd divided by 18. Oh yeah, forgot which example we were on, sorry. So what's easy math here? Sort of easy math. Yeah, the 18 to 33 goes roughly how many times? Kind of like twice. I would do that, right? Because I would say 18 times 2 is 36. So roughly this is going to go twice. But I know my answer is going to be less than twice, right? For sure, definitely less than twice. So since it's 18 into 33, then it's really 18 into 336 is like 20 times. Yes, we all just followed that. If you don't want to do it that way, then you move your exponent and you make it a 24, and then it's 2 times 10 to the 24th, but it's going to be less than this. So then you check your answer on your calculator, and you should get, 1.9 times 10 to the 24th molecules, which is what we said, less than 2.2 times 10 to the 24th. How many of you got that, not 550? Okay. So you know if you're struggling with the mental math, you need to see me. I bet you can guess what one of these answers coming up might be. All right, not this one, though. This one should be quick now. Look at what this asks you to do. Now it's asking you the same exact example, 56 grams of water, but now how many hydrogen atoms? Do you see how the unknown substance does not match the known substance? The unknown substance is hydrogen atoms. The known substance is water. So hydrogen atoms and water don't match. What is this? I know, what kind of particle? Like out of those 4 particles? It's a molecule, right? So when we go to solve, we're first solving for molecules we already did. It was 2 times 10 to the 24th, roughly. Now I'm just going to figure out how many hydrogen atoms there are. How many do you think there are? 2 of them, but what's the answer to this? It should be sort of quick. We know the other answer was 2 times 10 to the 24th molecules of water. How many hydrogen atoms are there? 4 times 10 to the 24th, because it's double the amount. Does that make sense? So here's the exact same setup as the last problem, isn't it? We got 2 times 10 to the 24th. Now you're going to add this last spot, which says, in 1 molecule of water, there are 2 atoms of hydrogen. So my answer is roughly 4 times 10 to the 24th if we did mental math. 3.7 times 10 to the 24th. Look at the sig figs, just pay attention. 2 sig figs here, 4, 4, unlimited, right? So then my answer can only carry 2 significant figures. All right, the next question, though, is just kind of, oops. No other next question. All right, moving on. The law of conservation of atoms, the law of conservation of mass, law of conservation of matter basically tells us that we can balance chemical equations correctly by just counting the number of atoms on each side. But some of you kind of forget that the mass is important too. The mass of whatever you start with has to be what's in your products also. So if you started with 50 grams of carbon, you need to end up with 50 grams of carbon. Now it can be distributed in a few areas. You might not actually physically weigh the carbon. It might have been lost to the atmosphere. But 50 grams of carbon went somewhere. So when you look at these, we balance for atoms. That's always true. But then we also can balance for mass. We'll use this tomorrow, Friday, when we do a combustion analysis sample, where we take the masses of the products and then we find the mass of the reactants. That one's a little bit trickier. But just recognize that law of conservation of mass quite literally means the masses. Next will be, predicting mass. Okay, so now we're going to do stoichiometry. This was the mole. Now we're going to stoichiometry. Can you look up here just for a moment? You need to remember that stoichiometry map is going from grams of A, 22.4 liters of A, 6.02 times 10 to the 23rd of A. All of these things can give me 1 mole of A. From there, I go to 1 mole of B, and then that can give me these 3 things. Grams of B, 22.4 liters of B, and 6.02 times 10 to the 23rd of B. So when you're following this, I'm starting with grams of methane, grams of A. I need to go to moles of A. Then I need to go to moles of B because water is a new substance. And then I'm going to go to grams of B because grams of B is my final product. So when you're solving these problems, I would map this out in my head, but you can also map it out on the paper. So if I'm looking at this, I can go grams of methane. It's going to go to moles of methane, and then it's going to go to moles of water, and then it's going to go to grams of water. Now these become automatically my top boxes, and I know how to easily cancel from here to here, and then I just have to plug in my numbers. All right, pause still. I don't want you to solve yet. What kind of problem is this? What kind of reaction is this? Combustion, right. So combustion you have to memorize. What are always your reactants? It's not in this problem. The reactant that you need is not there. What's always involved in a combustion reaction? Oxygen, right? And it always produces CO2 and water. So if you forget that, write that down. Combustion is always a hydrocarbon plus oxygen, and it always produces carbon dioxide and water. So it's a hydrocarbon plus O2 always gives CO2 plus water. How do you know? One of your key words here is burns. So burns essentially means use O2. Sometimes it might say explodes It might say combusts, ignites. Those are all kind of clue words that you need to use oxygen in here. All right, the last piece of information comes from this spot here. When you see moles over moles, here to here, that's this spot here, where do you get these numbers from? Right, from the coefficients in the balanced equation. So the first step to always doing a stoichiometric problem is to balance the chemical equation before you begin. All right, so everybody has to write out the reaction first, then balance it, and then we can do the stoichiometry. So give yourself a minute to do that. So after you set this problem up, I think you all probably had the same setup, but then we needed to solve for it. So without a calculator, you should be able to estimate somewhere in the 500 range, knowing that your answer is going to be kind of 550. But this is me assuming that the multiple choice answers themselves are spaced far enough apart that you didn't need to do such significant math. But always look at the answers before you do your math to know, do I need to be really careful, or can I just estimate this in the ballpark? So say these were just ballparked answers, you need to come up with the roughly 500. So do 250 essentially times 2 is 500 times 20, that would give me 10,000. And then that's divided by 16. I could certainly do this a little bit more, but because I rounded there, I was like, oh, I'll just round here to 20 and my answer is going to be roughly 500. So if I did this divided by 20 instead, it's like 2 into 1,000, which was 500, right? So my answer I got was approximately 500, but I knew that it should be much greater than 500 because I rounded so high up in my denominator. Now, if you had to be more careful, then of course you would do more math with the 16. And then you would spend more time. But I think just ballparking it, that should take quick seconds to do that kind of math, okay? All right, predicting mass of products. This is still stoichiometry. Still stoic. But this time it's asking you to predict the mass of 2 different products. Does that change how you approach the problem? It's just now 2 separate problems, and you're starting with the mass of the reactant and going to both carbon dioxide and iron. So step 1, always write a balanced chemical equation. Step 2, solve for the masses. So you're doing 2 stoichiometry problems. So I'm going to leave you like 5 minutes to sit here and do this on your own without a calculator, estimate your answers, and then try your answers with the calculator, okay? I'll walk around. All right, let's take a look. If you have the correct balancing, you should have a 3 and a 3 and a 2. You might have just written in a different order. And then find the masses of CO2 and iron. So you should have essentially the same setup up until your moles of iron and your moles of CO2, and then their masses will change here. So with a calculator, you should definitely have gotten this for 3 significant figures. Without the calculator, now you're estimating the math. Does anybody need help with that math estimation? Did you try it? Did you get it? Give me a thumbs up if you estimated one of these at least correctly. 2 people?
I'm still in the process. I just finished balancing.
You just finished balancing?
Yeah, he's riding.
Oh my goodness. I'll come by and help. All right, so in this first problem, you should eliminate your 3's, right? So that you don't have to worry about them. So then you're going to do 114 times 44. So what did you estimate? What do you want to estimate this to be? Choose something. Anything? 120 maybe? You could stick with 114 and make this 40. I don't know. I probably would do a 120 and a 40, just because that makes it a little bit easier on me, roughly. So then you just multiply that, and then add your 0, and then divide that by 28. Does that seem a little bit easier to do? So what would this be? Roughly. 28 times 2 would give you 56, right? So this is definitely too high. 48, so let me just show you something. If I do 28 times 2, I would get 56. If I do 28 times 1, I get 28. 48 is like 10-ish in between here, right? It's like halfway in between. So I would estimate that my answer is probably somewhere around 1.5-ish, but recognizing early on that I rounded down here, right? I took 44 and I rounded it down. Do you see that? So my answer is probably a little bit higher than 1.5. So if I did 1.5 into that, then my answer would have to be about, it would be greater than 150. And it's 179. Remember, I'm not getting exact answers. I'm looking for ballparks. And I'm trying to do as little math as possible to get there. Questions on that? This little process here is just trying to figure out, like, I don't want to say it's 200, and I don't want to say it's 100, because 48 lies somewhere in between there. And remember, 48 is too high anyway. All right, the last part there, try that without a calculator, multiplying across the top and dividing by the bottom. When you use your calculator, though, make sure that after you multiply across the top, you hit equals and then divide by and use parentheses in the denominator. Otherwise, your calculator may give you an incorrect answer. So everybody, if you did not try your calculator yet, try it at least for this last problem to make sure you're getting the 152 and not coming up with the wrong answer because you don't know how to use your calculator. Okay, so with your calculator, did you get this? No problems. All right. Obviously, the math was all here. You could try it without a calculator anytime you want to see if you end up with the right answer. All right, moving along. So the next piece that we need to learn, we're going to skip this one, okay? I'm going to put the answer up here for you. The only point of this slide is making sure that you recognize that I can give you one of your products, and you can calculate from the beginning how many reactants to use. So you can use reactants to products, or you can go from products to reactants. It doesn't matter which way. So we're just going to skip that one. You could jot the answer down as 51 grams of sodium bicarbonate. Recognize that this HCO3 bicarbonate is actually this polyatomic ion, right? That was something we did yesterday with hydrogen sulfate. We can call that bisulfate. We can call this bicarbonate. So the answer is 51 grams of sodium bicarbonate. All right, but we need to practice, for the sake of time, limiting reactants. So in a limiting reactant problem, the way that you will know that you need to do limiting reactants is that you're going to have two masses of your reactants to start. Jot that down. You must recognize it. You're always going to have two masses of reactants to start. Then you'll say to yourself that you need to do a limiting reactant problem. If it's only one mass of a reactant, then it just means the others are in excess, that they're not necessary to worry about. But when you have two masses, you have to do a limiting reactant. The limiting reactant prevents you from making any further product. The excess is always what's left over after the reaction is complete. So my approach to these problems, those of you who have had me, I always taught you to do it a certain way, which logically doesn't necessarily make sense. Thank you. Those of you who didn't have me probably did it a more logical way, but you spent much more time. So those of you who didn't have me, pay attention. I'm going to teach you it the non-logical but short way, because on multiple choice problems, you don't want to solve a problem out twice. That's how you learn to do it, right? Take your first reactant and go to product, take your second reactant and go to product, and whichever one's smaller is limiting. Is that true, boys? Yes? But the way I'm going to teach you to do it is to just look at your masses of your reactants and convert to moles, and then just compare your mole ratios to each other. So step one, I'm going to write these down for doing limiting reactant my way, is you always have to balance your equation. Step two, convert to moles. Convert grams of both to moles. And a lot of times on the AP exam, they're going to give you moles of the substance to start, if it's a multiple choice question. And then number three, divide moles by the coefficient in the balanced equation. And then here's how you solve. The smaller number is limiting. You don't use that number for anything. You just recognize, oh, that one's my limiting reactant. Then solve the problem with the limiting substance. So you're essentially just solving in the beginning for which one you're going to use. This prevents you from doing two huge problems if it's just a simple like multiple choice, which of the following is the limiting reactant. You could just do this by looking at moles to what is necessary in the balanced equation, moles to moles essentially. So let's take a look at this example, and then I'll show you the work. If you want to do it the long way, or the way that you learned in your other class, you're welcome to do it that way. I'm not going to change your technique. This is just a shortcut, essentially, to getting to the same answer. So if you're doing it with me for my way, what I would do is I would take that 28 grams, oh, you don't know what glucose is, C6H12O6. Let me put up the balanced equation first. There it is. Let me move this down. So I would take my 28 grams of C6H12O6, and I'm going to convert that to moles. So let me just double check that mass. It is 180.18. All right, so I'm just going to do this on my calculator and show you. You don't have to do anything, just follow along. So this is going to give me 0.155 moles. I guess for sig figs, 0.16 moles. Then I'm going to take this many moles and divide it by the coefficient in the balanced chemical equation, which will be a 1 when it comes up. So there's 1 mole there. So my answer is still 0.16 moles of glucose. Then I'm going to take my 14 grams of oxygen, and I'm going to convert that to moles. So 32.0 grams of O2 is to 1 mole of O2. I put that in my calculator. Whoa. And I get 0.44 moles. And then I divide this by the coefficient here, which is a 6. This gives me 0.073 moles of O2. So which one is smaller? Clearly this is smaller, right? So then my limiting is definitely O2. So if this was a multiple choice problem, do you see how much work you just saved yourself from doing? You didn't have to convert all the way from grams of glucose to grams of CO2, and then grams of oxygen to grams of CO2. That's how those of you who didn't have me learn to do it. You go from the very beginning to the end for each of them and then compare. Now, all I'm going to do is start my problem with O2 as the limiting, and I'm essentially just going to do the stoichiometry from this point forward. You don't use this number for anything else. At this point, it just told you which one was limiting. You don't keep using it for anything, okay? You just essentially start over. Now, those of you who are smart enough can recognize that this is the stoichiometry to go from moles and 6 here, then you can go and continue the problem on. But sometimes that just gets confusing. So just start the problem with the limiting reactant. So now we're going to try it. This is how you would have done it if you didn't do it with me. You would have done this whole stoichiometry problem out and you would have gotten 41 grams of CO2. But since you did do this with me and you recognize that the limiting was O2, then this is the only piece that you would have done. You would have just done 14 grams of O2, you would have done the stoichiometry, and this comes from the mole-to-mole ratio from your balanced chemical equation, times the molar mass, and you would have gotten 19 grams. So you wouldn't have had to do any of the other math to find that answer. If you choose to do it that way, though, you still can. All you do is compare your answers at the end, and whichever one gave you the smaller answer is your limiting. But we figured that out like 15 steps ago, right? We didn't do all of that other math. Any questions with that? You're going to have a ton of time to practice this tomorrow. That's why limiting reactant is probably just the hardest part. If you could do a limiting reactant problem, you can do any stoichiometry problem because you're doing stoich. All right, the very last slide is how to do percent yield. What is percent? Okay, here we are. 5 times. So percent yield then is always going to be the part that you got over the whole, which you should have got. So theoretical is what you should get, and you get this number on paper. That's what I say. It's like my paper number. Like I'm going to do a lab, and I'm going to calculate how many grams of whatever I should get, but this is what I actually get from the lab. This is always going to be given to you in the question, because you're not actually going in the lab and doing anything, so the question has to tell you this is how much you got. So like say you were supposed to get 100 grams of your product, but oops, you're a terrible chemist and you spilt half on the floor. So now your percent yield is 50 grams over 100 grams, 50%, right? So actual is what, in the end, what do you have to give to present to your boss? Like, hey, look, I made 1 gram out of the 1,000 I was supposed to get. Okay? So always is part over whole, actual over theoretical. The other calculation that we've done before is percent error. That's actual minus theoretical absolute value over actual times 100. You're not going to have to do that often, but this one you will do quite often. Any questions?